What if you could design really complex machinery just by, well, drawing pictures? Today, we're going to dive into a powerful technique that lets you do exactly that, probably using software you already have on your computer. It's called Geometric Constraint Programming, or GCP for short. All right, so here's our game plan. First, we'll talk about the big challenge that engineers have been wrestling with for decades. Then, we'll introduce GCP as the amazing solution it is, break down how it actually works, and of course, see it in action. And finally, we'll see why this whole idea is way more than just a tool. It's a totally new way to think about design. So let's start with the why. Why do we even need something like GCP in the first place? Well, for a long time, designing things like linkages and mechanisms has been a real headache for engineers. And this quote, man, it just sums it up perfectly. To figure out the exact position of a linkage, you have to solve some incredibly complex and, as the author says, nastily nonlinear equations. Trying to do this by hand is not only tedious, it's just asking for mistakes. For the longest time, the other options weren't much better. You either had to rely on these painstaking graphical methods on paper, or you needed access to these crazy expensive specialized computer programs that most engineers and, especially students, just couldn't get their hands on. But here's the good news. All of that has changed. Modern CAD software has given us this really elegant and, most importantly, accessible solution to this old problem. And that solution is geometric constraint programming. The core idea is actually super simple. You use the 2D sketch mode in the CAD software you already know, like SolidWorks, Inventor, or Creo, to solve these really complex kinematic problems visually. You just draw it, and you let the software handle all that nasty math in the background. So what's happening here is that this technique literally transforms a simple, static drawing into a dynamic, intelligent graphical program. Your sketch isn't just a picture anymore. It becomes an interactive tool for solving problems. Okay, so how does this magic actually happen? Well, it all boils down to the fundamental building blocks of GCP, and those are geometric constraints. And this is where it gets really cool. You're no longer the mathematician crunching all the numbers. Nope, you become the director. You just apply simple, logical rules to your sketch, things like, hey, these 2 points have to touch, or this line always needs to be vertical. And the CAD program's powerful solver, it does all the heavy lifting for you. The language you use to direct the sketch is made up of these really simple constraints. A merge constraint, that creates a pivot joint. A fix constraint anchors a point to the ground. Equality just makes sure 2 links are always the same length. On their own, they're simple, but when you combine them, that's when they become incredibly powerful. Now, this right here is how you program the sketch, and it's absolutely crucial. A driving dimension is your input. You set a value, say 4 inches, and that becomes a rule the sketch has to follow. A driven dimension, on the other hand, is your output. It doesn't set any rules, it just measures and tells you a value based on how the mechanism moves. Getting this input-output relationship is really the key to the whole thing. Okay, theory is great and all, but let's make this real. We're going to build a simple 4-bar linkage using these exact principles. Let's see it in action. So we start here, and right now, this is, well, it's just a dumb sketch. It's a few lines connected together. You can drag any point, any line, anywhere you want. There are no rules, no relationships. It is definitely not a mechanism. Yet. Okay, now we bring it to life. We start applying our rules. First, we use a fixed constraint to nail down a ground pivot. Then, we merge the endpoints of our lines to create the moving joints. And finally, we use dimension lock to tell the sketch exactly how long each link needs to be. And voila! Look at that! Our simple, dumb sketch has completely transformed into a fully functional, totally predictable 4-bar linkage. We can grab the input link, drag it, and watch the whole thing move exactly how it's supposed to, following all the rules we just gave it. And the best part? We did all of that without solving a single trigonometric equation by hand. But here's the really important part. We didn't just build a single mechanism. We've actually built a program. So let's see what that really means. This right here, this is the big payoff. Because our drawing is now a system of rules, a program, we can change our inputs, those driving dimensions we talked about, and the software will instantly calculate a totally new, valid solution for the entire mechanism. It's incredible. Check out this fantastic example. On the left, we've got a solved double rocker mechanism with very specific link lengths. Now, what if we decide that output link needs to be shorter? Instead of pulling off your calculator and starting all over again, you just change that one driving dimension, and instantly the system resolves itself into the brand new configuration you see on the right. And just look at the numbers. All we did was change the output link from 2 inches to 1 inch. But the program didn't just shrink that one part. It automatically recalculated the new required lengths for the input link and the coupler to make the entire design work again. This turns what could be hours of tedious redesign into a single, simple edit. It's a game changer. All right, so let's wrap this up. What does this all mean for you? What's the big takeaway from all this? The most important thing to remember is that this isn't some futuristic, expensive technology. Geometric constraint programming is a technique. It's a way of thinking that unlocks the incredible power that's already built into the standard CAD software that so many of you are already using every single day. It's a superpower that's been hiding in plain sight. This method turns static sketches into dynamic solvers. And yeah, it's amazing for mechanisms, but think bigger. This works for pretty much any problem that you can describe with geometry and a set of rules. It's a fundamental shift in how we can approach problem solving. So the question I want to leave you with is this: what other complex challenges could you solve by programming with pictures?